Welcome to Algebraic Geometry Codes. This is one of the courses I like to give most, maybe the course I like most, so don't tell the other courses. The entire board is going to be mathematical. It's going to be on the board. We are not going to use slides, but just for today and maybe half an hour next week, because this week we are losing half an hour, if you remember, between 12 and 12:30. Let me just do this kind of boring part and maybe some of the interesting, but not that interesting part on the board. Let me just talk about what this course is about. Tells us a few words about Tomer, your TA, and myself. What are we doing as researchers? And then some, bureaucratic information about grades and stuff like that, and how do we proceed, and see a little bit of history, the original paper that kind of initiated the whole thing. So yeah, so this course is about error correcting codes. Have you seen? Do you know what an error correcting code is? More or less. Yeah. So, but this is not a course about error correcting codes in the sense that we are not going to study like in breadth the whole theory and the lower bounds, upper bounds, constructions, techniques, blah blah blah. It's very interesting, but we are not going to do it here. We are going to do something that's much more interesting. We are going to consider only one construction of a code, like a family of codes. They are called sometimes GOPA codes because Valery Gopa is kind of the first person to point out the idea of using algebraic geometry in order to construct codes, or they are also called algebraic geometric or algebraic geometry codes. I don't know exactly what I should say. Some people use this and that phrase. Anyhow, let me just start saying from the beginning, this is the most beautiful construction I've ever seen in any like construction of anything in mathematics. Okay, it's really, really, really elegant and beautiful and deep. Not only that, do you know what is the probabilistic method, for example? Most of you, some of you, yeah, well, yeah. So maybe for those who don't, the probabilistic method is a way of proving the existence of an object that we care about without giving us any effective way of constructing it. So it does something for us. It proves the existence of some object, and in that it also tells us what are the parameters that we may expect, like the size of the object or whatever. But it's kind of annoying because it doesn't give you a construction. So you don't have like a way of describing an object that has the same parameters that the probabilistic method guarantees to exist, okay? In mathematics world, it's an ineffective proof technique. But it's usually almost always optimal or very close to optimal. So the lower bounds that you can sometimes prove are sometimes almost always tight, sometimes are like epsilon far away from tight, but there are only like 2 or 3 nice, good examples, interesting examples. They are weird examples, but good examples in which the probabilistic method like fails. And it usually means that the problem has more structure than you kind of imagine to begin with. And algebraic geometry codes is the example. It's the most most interesting example, both quantitatively and kind of philosophically. Like the codes that we will construct are much better than the random codes that you have. And those random codes go by the name Gilbert Varshamov. These are 2 people that kind of used the probabilistic method maybe 70 years ago to prove the existence of codes. One for linear codes and the other for general codes, but never mind that. So that's a very interesting point. But before even starting to talk about this code, and sorry, please stop me for any question and so forth, like the usual, okay? I kind of really mean it. Do stop me for any question. But before, let me just introduce myself and Tomer. So I'm doing, well, I think I'm doing complexity theory, even though I'm not doing like P and NP. I'm a complexity theorist, essentially, but I'm mostly working on problems related to randomness and related questions like BPL versus L and stuff like that. And when you study those things, you usually have to construct objects that are pseudo-random. That's the second bullet here. You want to construct graphs that have certain properties or functions like codes and so forth. And you can't help but doing some coding theory. So I'm not a coding theorist per se, but you can't avoid doing some coding theory or using some coding theory and so forth. And that's where I learned about AG codes, of course. Now, I don't personally care about the codes that you get from the algebraic geometry techniques. I care about the techniques and hope that they can be used to solve other problems we care about. Okay, that's my agenda. Okay, my long-term agenda. No one believes me, like it's going to work and so forth, because it really didn't quite happen so much yet. And I will explain why I think it didn't happen, and you are part of the solution. Okay, not knowing that, but you're part of the solution. Now, the thing about pseudo-randomness is that there are two kinds of things you can do, essentially. You can either use polynomials or the stronger version, algebraic geometry stuff, or you can use graph, and that's the fourth bullet, like the expander graph usually. So a spectral graph here is something else I'm doing. It's kind of not orthogonal, but it's not like completely related to what we're doing here. So maybe last semester I gave a course about free probability and kind of spectral graph stuff. And so this is now my other face, the one that likes polynomials and algebraic geometry. Okay. Tomer, which sits here, will be your TA. He's my PhD student, and he does AG codes. Okay. Try to use AG codes to do something to solve interesting problems that we don't know how to solve. Questions about maybe us? No, I guess not. Right? Course mechanics. So yeah, so that's the really boring part. That's why it's on slides, so that we can briefly skim over it. So we are going to meet here. I mean, if you're here, you know that. So we're going to meet here at this hour. And Tomer's recitation, you'll have 1 hour kind of a break to think of what happened in the first 3 hours, and then Tomer will have a recitation. I'm not going to have a reception hour. It's not an undergrad course, but I'm sincerely will be happy to meet if you want to. So just email me and we'll find time, okay, to talk about questions or problem sets or material or whatever. Okay, and as I said, I'm going to record the lectures, and Tomer is going to record the recitations, but please don't use it as a reason not to show up. It's better to show up. And I'm going to do it in English, just so that people that don't know Hebrew can also enjoy it. And we are not going to connect via Zoom, okay? It's just disruptive for the course. There's going to be a course homepage. We are not going to use Moodle, except for maybe for the grades. So everything is going to appear here, the notes, the homework, and essentially that's it. This is my email, this is Tomer's email. These notes appear on the course homepage, which is kind of recursive because the homepage appears here, and so forth. The grade, okay, so half of the grade will be based on the homework. We are going to put out like 5, maybe 4, maybe 6, but probably 4 or 5 assignments. You're going to submit them in pairs. You can submit in individuals, but you can submit them in pairs. It's really important to actually do them because it's a mathematical course. It builds upon what happened last time, kind of heavily. So, we are only going to grade some of the questions because Tomer has research to do also. And based on that, there's going to be the grade. And the other half, we're not going to have an exam, but the other half is going to, that's my favorite part, is going to be a 1-hour presentation that you're going to give. So we are going to leave out some of the subjects that I would have wanted to talk about, but time constraint won't allow us. So you're going to, it was very successful last time. I learned a lot. So you're going to choose a topic and present it for 1 hour, like 50 minutes. So it's kind of flexible. And it's actually very nice. It's also nice if you come to other people's talks. You don't have to, but it's less nice. Only I and Tomer sit there, but okay, long time from now. So never mind that now. Okay, literature and the notes and stuff. So I'm going to use the whiteboard. I wrote blackboard by kind of accident. I'm going to use the whiteboard throughout the lecture, except for this one, so that I can make it like slower. Last time I actually gave it on the slides, using my slides that are available on the web page, so you can actually see them if you want. But it was too fast, so I think the board will slow me down, and everyone will be able to grasping more slowly. And the downside is that I won't be able to prove everything. So I'm going to leave out proofs that I don't think that are that insightful, like the trade-off between how technical and time-consuming they are versus insightfulness. is bad, so I'm going to leave them out, but they appear on the notes in full, so you can skim out for them. I'm not going to skip like a whole thing, just maybe little lemma here and there, which I don't think is crucial for your understanding. Even though I kind of, my belief is that you kind of have to see everything, but choices. What can I do? And maybe if it will be that bad and I'll kind of skip too much, I'll put a video of a proof that I should have done and didn't, and won't just tell you it appears on the notes, okay? But I hope we won't get to that point. I hope that everything I want to say, I'll be able to say here, and that's it. We'll have notes. You don't have to consider any outside reference. You have all notes sitting on the course homepage. They're actually ready. They're all there in the previous instantiation of this course. You can look at it on my homepage, but I'm doing some editing. Actually, I'm not sure my editing is helpful. I think last time I was kind of better, but see. So you don't have to consider outside references, but there are some, so let me tell you about them. So Dan Haran from math here gave a course about algebraic function fields. He didn't care about codes, but it's kind of the same underlying math. It was a really good course. I took it. It was in COVID, so it was Zoom. Annoying, but still amazing. And actually, like maybe 2/3 of this course is that course, but shrink to 2/3. So we are going to follow his lecture notes, and there is a link. Actually, the PDF itself, because the link is broken now, appears on my own page. Okay, so you can see that it's in Hebrew. That's the downside for those who don't know Hebrew. And the kind of the reference for this course is the book by Stichtenov, which is called Algebraic Function Field and Codes. It's this one. You can find it, say in the library, or PDF versions in the library, and so forth, like e-copies. It's not hard to find. But there are other books, so you don't need to follow. You don't need to actually look. Everything is in the notes. But if you want, you can do that. We're actually kind of going to cover everything there. There are other books. It's kind of funny. We're not going to cover them as well. There's this one. I don't know if you can see, but like the font itself is like typeset weirdly. So that's like it's Fassman Vladut book, to Heroes of Algebraic Geometry Codes. So they wrote it in the 90s. Yeah, I think in the 90s, maybe 10 years, 91, 10 years after Gopa kind of published the paper or gave the talk about the idea that he had. And then they kind of had a second book, which is this one, but it was published 10 years afterwards. And this is like twice the time the field appeared. So here there are more results and kind of better explained, in retrospect and so forth. And then 10 years afterwards, they published the advanced chapter, which I'm still kind of struggling with. So let's not go there, because if you ask me about that, I won't know more than half. And then there is this weird, very nice. No, the book is not weird. There is a weird story, and this book is very nice covering it. This is a kind of a math history book, not a math book per se. There is a paper, a very important paper by Dedichen and Weber. I will talk about that soon. It's in German, but not only it's in German, it's very succinct and maybe hard to really get what's going on if you don't have the context. And since we don't live 150 years before now, you won't have the context. So this book actually has its fourth chapter. It gives the history for that paper, and then in the later chapters, it kind of like when you have the Bible and there are the Perushim. So they do that. They kind of explain the Bible better. Anyhow, it's a very nice book, but only if you're going to love the course, you want to look at it. But it's a kind of an if and only if. Okay. Questions about that? Good. So prerequisite. Okay, prerequisite is actually a delicate thing here. So first of all, the name of the course, I think it's like Algebraic Geometry Codes. So you may assume you need to know both algebraic geometry and codes. So you actually have to know neither, okay? But what you pay is what you get. You also won't know like coding theory per se or algebraic geometry per se. I'm not going to teach two courses in one course. And algebraic geometry is not really one course, a subject, and you should usually take two courses. So we are going to, I'm going to explain in what sense, but we're going to use some part of algebraic geometry, algebraic curves, if you know what that is, only dimension one, to construct codes. So we don't need to know all of coding theory or all of algebraic geometry in order to do so. And in fact, that's the hard part for me. I mean, the right way of teaching this course is to know coding theory and know algebraic geometry. The intersection is quite small, probably the size of this class, like in the world, okay? And then it's kind of a, well, it's a corollary. Once you know what you want from coding theory and what are the available tools in algebraic geometry, after Gopa kind of whispered in our ear what you should do, it's not so hard. It's like maybe half a course to do, okay? But the point of this course is that I want to teach you algebraic geometry course, even if you don't know algebraic geometry. The codes part is not difficult, what you need. So the algebraic geometry part is going to be missing, and I still want us to understand everything. Because of the history of the way these things were developed, there is almost no geometry. Like the geometry was taken out from kind of algebraic geometry, and the algebraic part is the one that's left. So we will only have to work with kind of algebraic structure. This means that, like, on the day-to-day basis, what we will do is we'll talk about fields and field extensions and rings and ideals, and from kind of the basic stuff. And mid-semester onwards, we'll need basic Galois theory, but I think of it as something more advanced. So maybe basic Galois theory. You'll have time to complement that until then. And if I'll maybe talk about a bit more about that. So these are the prerequisites that you should really have. But don't worry about that. So here we are. Okay, we need to talk about algebraic geometry codes. And I don't know, you would imagine you need algebraic geometry, right? And also code, but I didn't even put it here, so codes. The part from codes that you need is really mine, so don't worry about that. And if you want to study algebraic geometry, codes, even if you know algebraic geometry, it's not enough. Because when you do algebraic geometry, like classical algebraic geometry, you work usually over the complex plane or some arbitrarily closed field, but something you don't mind about the field itself. But it's better to be algebraically closed. And in algebraic geometry codes, we are going to work over finite fields. That's we need finite elements in the code. So the structure of the field, the arithmetic of the field comes into play, and that's why in algebraic geometry codes, you also use ideas from algebraic number theory. Actually, maybe more ideas from here than from here. So maybe that name is a bit misleading. Okay, so what we need from algebraic geometry is not too much. It's only algebraic curves, so it's a full course, but that one course. And from algebraic number theory, we need ideas of Dedekind domains and so forth. And factorization of ideals and stuff that may not tell you too much now, but at this point. But really, what you will need. So if I want to talk to someone over coffee about what are these things with competition, he needs to know these two things. Now, in order to learn any of them, you need to know topology, commutative algebra like rings and all types of stuff about rings, but only commutative, but still. And also, you usually start with something which is geometrical, like Riemannian manifolds or something, and definitely complex analysis, which I kind of left out. And you need also Galois theory for this, less for that. Okay? So I'm assuming you have none of those, except for Galois in the mid-semester. Right, so I'm doing you a huge favor here. I'm erasing half of the, like 3/4 of the prerequisite to the prerequisite. And that's my excuse for the fact that you don't see algebraic geometry codes, the math of algebraic geometry codes used in other problems. Because you need to know a lot, and it's also not so easy. It's not just a lot. It's kind of difficult. So the steep learning curve kind of prevents like people like me from doing that usually. And that's why the intersection between people who understand what are the important problems in theoretical computer science and people who knows all of that is small, and that's why you are part of the solution, because now it's doubled essentially, okay, if you're going to stay. Questions? Yeah, actually, maybe that's how it's a bit, yeah. more to algebraic geometry. Yeah. Yeah. And maybe you should put the Galois theory a little bit at some point to algebraic geometry also. So when you cover stuff. So I don't know. Yeah, maybe you should switch two arrows. And I definitely should have added the complex analysis course here, which kind of should point here and in the intuition to everywhere else, essentially. But the point is that you don't have to know all of that, okay? There is a price for that. First of all, you should know, and you're in your 20s or something, when you reach your 40s, like me, you should know all of that, okay? You shouldn't like live your life without knowing those. But I'm just saying you can start living your life without knowing those things. The price is that someone who does know algebraic geometry, at least that point, has a intuition that is hidden when you only do the algebra. Right? We are going to do a lot of algebra, and I mean, some people are just fine with that. They don't care about geometry. I don't know. That's my intuition. For example, the previous TA, Shir Peleg, she was like fine with the ideas. She didn't like the geometry at all. But I think most people have these kind of pre-ideas about what's a curve is, even if I don't tell you what it is. And they imagine it, even though it's over a finite field, so the imagination is not quite the right thing. But so you won't have, like, we are not going to rigorously connect geometry to algebra, but I'm always going to tell you, at least at some informal level, just to keep your intuition like following the algebra, I'm going to tell you what's going on in the geometric part, okay? So if you only care about the geometry for the intuition, then that's what we'll do anyhow. But there is a connection, a formal connection between the geometric and algebraic point of views on the same object. And it's maybe premature to talk about it, but just know that there is a little bit of a price to pay. What can you do? Yeah, so that's what I kind of wrote here. So just to know what's written. That's what I said here. Okay, so how do we proceed, unless there are any questions so far? Okay. I just for curiosity, someone knows some of these things? Like, yeah, okay, good. So I may hint, I mean, sometimes you're going to see something here, those of you who know those things, and it's going to seem familiar to something you learned in commutative algebra or something, and I won't be able to stop myself from saying, note, by the way, that this is like a localization of this ring or something, just to connect the dots for you. But when I say those things, I'll kind of put a flag on, don't listen to me if you don't care, for like 5 minutes, 5 seconds, and then I'm going to go back and talk to everyone, okay? But you should really know commutative algebra. I mean, you can't live like that. You can, it's like, it should be part of life, okay, your life. Definitely topology. Okay, so how do we proceed? So this is the plan for today and the rest of the course, maybe more for the rest of the course. So first of all, I'm going to give you a kind of a quick and dirty introduction to coding theory. How many of you saw Reed Solomon, Reed Muller codes? Okay, so yeah, you'll have to see it again, but very kind of quite quickly, okay? I'm only showing you that because we need to understand the question that we are trying to solve. This is a one question course. We are going to solve one question, but in a beautiful way, and the techniques are going to be hopefully useful elsewhere. So we're going to see Reed Solomon and Reed Muller as a motivation for GOP as idea of algebraic geometry codes. I'm going to do it on the slides, even though maybe it's better to do it on the board, but because it's kind of easy, so I rather kind of spend more time on the hard parts than the easy parts. So that's going to take an hour today, and then I'm going to start talking about the basic of algebraic, the basic of the theory. I kind of didn't give it a name here, but it's called algebraic function fields or algebraic curves, depending if you are a geometer or algebraic person, algebraists. So the first thing I'm going to do is informally, and this is on the slides because it's informal. It has like math symbols, but it's informal. An informal introduction to an informal way of, we are going to informally discuss how to abstract the notion of a point. Right, so a point is like, I don't know what you have in mind when you hear geometry, but points are going to be there. Right? You have points. Maybe you have distances, or maybe you don't have distances, but points you have. So we are going to abstract the notion of a point in like 4 different ways, 4 algebraic ways. And if I'm going to just give you the definitions, like the dry definitions, I don't know if it will do the job, so I'm going to do it informally, like half pseudo-formally. Next time we're going to start doing anything formal, but that's what we're going to do today. Then we're going to talk about function fields. It maybe says nothing here at this point, but this is a very important, the title of every book there, so it's something important. And we are going to continue to talk about things that I can't really say right now because they won't have any meaning, like divisors and so forth, until we reach the point in which we are going to prove Riemann's theorem. So I guess you heard about Riemann, right? Riemann's hypothesis and stuff like that. He's a famous guy. And like 100, well, I don't know, 80, 70 years ago, he proved a remarkable theorem that is a theorem / definition. That theorem enables you to define the definition, enables to define the genus of a curve or a Riemann surface in his language. So have you heard about this? The name, not from like biology, but yeah, okay. So actually it comes from Darwin. Like Darwin kind of ruled, like people on coffee talked about Darwin's ideas, and genus is the way kind of right of splitting, like a kind of a rough way of splitting the living creatures or whatever. I don't know about that too much. And so genus is the way of kind of categorizing in a rough way the algebraic curves or Riemann surfaces. So we talk about the genus. Maybe you heard about it. It's kind of the number of holes and so forth. In a donut, you have 1 hole, genus 1. And so the remarkable theorem about Riemann's theorem, not the way he proved it for the complex numbers, but the remarkable thing that happened later, where people actually generalize that to any field, is that you can define genus non-geometrically, just algebraically. And when you go to the complex plane, go back to where you used to live, and it coincides with the original definition. Okay, so anyhow, only at that point, I can even say what the codes are, not analyze them or anything. We can just have this language to talk about it. And you'll see, I'll have a short screen of Gopa's paper in a second, and you'll see, I mean, we don't have the language to say what's going on here. And not only that, actually, it's even worse. So Gopa code it's not a code, it's a family of code. It's a way of taking an algebraic curve and functions on it, and take that into a code. So Gopa code is that process. If you want to get an actual code, you want to find an actual curve that has properties that you want. So Gopa code is not a code, it's a way of translating algebraic geometry to coding theory. And that's what, at this point, this is maybe the 5th lecture. At this point, we'll have that. And we will algebraic geometry course only on curves in that theorem, or an extension, an important extension of that called Riemann-Roch, which I'll talk about in a second. But usually that takes like 14 weeks if you do it with the geometry. So that's why I can't do the geometry, because I don't want to end the course with telling you, like, you should take another one, right? Because we just defined the codes. We ended up with a definition, not with a construction. It's kind of, it happened to me once. I gave a course like that and ended like that. And yeah. So then in the second part, the longer part of the course, we are going to kind of deepen our understanding of algebraic function fields, algebraic curves, and we're going to prove the Riemann-Roch theorem. Roch was a student of Riemann, and he was able to, so Riemann's theorem is an inequality. It tells you that some subspace has a dimension that is not, it kind of bounds the dimension of that subspace. And so Roch was able to kind of find the missing part. He was able to tell you the gap, the difference between two numbers, is actually a dimension of some other vector space. And it's crucial. That's like one of the, like, I don't know, definitely one of the most important theories in mathematics. Okay, it's like a really important theorem. it goes way beyond like what we need. Okay, so it's a fantastic theorem. I think both of them kind of died young, and that's why you never heard about Roch so much. Maybe it's okay. You don't hear about it too much. It's not his fault. Okay, so it's not like after he proved that he kind of went on vacation or something. He just wasn't that lucky. And after that proof, that's usually the accumulating point of a course in algebraic geometry curves. We would want to actually construct curves that will give you good codes. And the way we are going to do that, there is another way, but I'm just going to mention it. We are going to kind of build our curves over another curve in a kind of very theoretical computer science way. And when you do that, with every curve, there's going to be a field attached to it. So what will happen is that you'll have these field extensions. So that's where Galois will come in. Okay, so we are going to talk about function field extensions. There's going to be, the groups that are attached to them, and we're going to understand the groups, and by that understand the function fields, and so the curves. And kind of remarkably, and maybe you would think I'm kind of, I don't know, crazy, we are going to prove the Riemann hypothesis. Kind of in this bullet, we're going to do more, right? But we're not going to prove the Riemann hypothesis like over the ring of integers, because that would be very interesting to do. We're only going to prove it, we're going to prove it over curves over finite fields. So I'm going to remind you what is the Riemann hypothesis and tell you that, you're looking at kind of the one Riemann hypothesis. There are more because you can switch the ring. And when you switch the ring from Z to the ring associated to a curve, then you can actually prove it. It's not easy, but you can prove it. So I think Artin, maybe you heard about it. If you did commutative algebra, you know Artinian rings. Raised this question, and Hasse proved it for genus 1, and Weil proved it in the general case. These are like big people, okay? And it's a remarkable proof, and it uses heavily the Riemann-Roch theorem. So here we are going to work with zeta functions and so forth. Really interesting stuff. It's actually not going to be too hard given the Riemann-Roch theorem. It's like a lecture. So just to appreciate how deep is Riemann-Roch. It's like most of the work in order to prove the Riemann hypothesis of algebraic curves. And actually that theorem is useful aside from coding theory, because once you have the Riemann hypothesis, you know how to bound certain what's called exponential sums, and that appears in many areas. So I don't know if you know about that. We'll talk about that when we get there. Okay, and then we'll do more stuff which I can't say because I don't have the language to say it at this point. And then finally, in the last hopefully 2 lectures, definitely 1, but hopefully 2 lectures, we're going to construct AG codes based on what we did. We're going to find good curves and extend them and understand using everything we proved, including most of the things here that in the 3 dots thing that you don't see here. We'll be able to understand the parameters of the code, the distance and the rate, but we'll talk about it in a second. And and that will be very nice. Questions? Okay, so forget about this quote. Let's look at Gopa's paper. So this is Gopa's paper. There is one, like, the least issue is learning Russian in order to read it. But my understanding is that it's not quite a paper per se. I think that he had this idea in 75 just for fun. In 75, and he gave a talk in 81. And at that talk, some person kind of sat and got something out of it. And he told Sfassman, and then Sfassman and Vladut and these other people were able to actually take Gopa's idea and make a code out of it. But that's the paper. And you see, even if you ignore the Russian, you have these like, I don't know, you can make sense of those things, I think, right? This is any guesses what this means? No, residues, right? It's worse. It's like, so when you do complex analysis, you have these residues, like it's related to the poles of the function that you care about. And so you see there are poles like in part of what looks the definition of a code, because you have brackets and commas in between and you output things. So yes.
without knowing Russian, like if you know the standard way of lettering things, you can understand what's written here.
Like
What's the view?
the words, not the. Yeah, good. So the words I will give you for free, but then the rest. And when it continues, it's nice. It gives you examples, right? I mean, you don't see an example. Like this is it's called the Fermat's curve, because it's with free, but x to the n plus y to the n equals z to the n or minus z to the n. You're over f4, so you don't mind. So I give you this example over the field of 4 elements, and he actually writes like the points in which you're going to evaluate when we're going to talk about it. But you see, there is an example. This square root of q, I mean, q is the field side, but the square root, like it's 1/2, that's the half in the Riemann hypothesis. That's a deep 1/2 that's going on there. Right, the Riemann hypothesis tell you that right, all the zeros of the zeta function lie on the real line with 1/2. That's the 1/2. But here it's proven. It's remarkable and amazing. Okay, I don't know, we're not there yet, but yeah, and then it does some other stuff. There are like numbers, like right? These numbers, I don't know, like an example. And then he talks about, right, this is another number, but that's actually a famous number. He talks about the automorphism group of a curve, and he proves it's at most 84 times the genus minus 1. That's a famous theorem. But anyhow, I just want to stress that we really need to kind of just start talking before we can talk about, before we can present the construction of the code. Okay, so questions so far about the introductory part? Okay. So maybe we'll switch to the next one. No questions, really? Nothing? Okay. So let's do the quick and dirty introduction to coding theory. At some point I should give a course about coding theory, but Amnon give courses now and then, so maybe Amir also, I don't know. So you can certainly learn coding theory. Or maybe I should also say, just as part of the introductory part, this is the course homepage. I don't know if I'm going up or down. This is the course homepage. And after the syllabus, okay, here you're going to have the notes. And if you're going to the previous instantiation, all the notes are there already. I'm not going to change too much of them. So if you want, you can look there, but I'm going to put it here, like week after week. And what's important for me is these video lectures. So I don't know, I like hearing, I don't like reading. I don't know why. There are many good video lectures. I'm not going to talk too much about them, but this, for example, is a really recently given course, like from 3 months ago or something, by Andrea Gaffman, and he gave the course about plain algebraic curves. It doesn't talk about codes. It only does algebraic curves, which is what we need, but he really emphasizes the geometric part. He kind of builds the algebraic slowly and surely, with almost no assumption in commutative algebra, even less than what we are going to assume. Like maybe the same. And I don't know. This is a fantastic course. Like, I mean, I know it, and I still saw it like 3 months ago because it was so good. Okay, so maybe you want to look at it. And then there's Nitin Saxena. Do you know Saxena? Someone heard about him? From where?
He does PAT.
Right, but now he does PAT. But when he was young, right, exactly. He proved that primes is in P. He is one of the authors of the AKS paper, putting primes in polynomial time. Nice result to have under your belt. And he gave a course that actually, so in this course, Andrea doesn't talk about, he talks about he doesn't care about the field. He talks about complex numbers or whatever. I mean, he doesn't talk about it because he doesn't care. As long as it's algebraically closed, it's okay. And here, if you care about the arithmetic of the field, and we care about the arithmetic of the field, this is another course that you can look at where they put more emphasis on that. And then there are other stuff, so I'm not going to go over all of them, but yeah, if you think you have some missing information, then maybe you want to look here as well. Okay, about commutative algebra or algebraic geometry or curves, but you don't have to. And this is a course about algebraic coding theory by Marie Wouters from Stanford, and she's a really good lecturer, and she just gives you the kind of a basic course about algebraic coding theory, like algebraic techniques used in coding theory, which is really nice to see if you don't know any of that. Okay. Anyhow, plenty of things to learn if you want.